Okay, it should be working now. Jeez. All right, so this is class 16, where we're continuing on with dimensional analysis and modeling, and I've entitled this section as Similitude. This is the second part, the second part of Chapter 7 that we're covering, where we're going to use the stuff we developed in Buckingham Pi for a purpose. And I didn't make my use my cartoon, so let me go back and fix that. Okay, so here's their stupid cartoon that I made on my iPad the other day, where we have Wedded, and he's looking at smaller versions of himself. Well, that's the idea here. So we're going to scale things, and we're going to make models. That was really worth it, right? All that effort, but who cares? So the idea, let me switch over to here. The idea is that we have the real world, and we have a lab, right? And we're going to make a model in the lab, and we're going to run experiments. And for the prototype, we had these pi terms. We have a primary pi term, and then we have like what we could think of as dependent pi terms. And there could be a lot of them. Let's say that there's n number of these pi terms. Well, over here for the model, we'll give them a subscript with an m and say they have all the same pi terms. Dot, 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 and there'll be nm of these, right? So what we have to say is over here, we have these modeling laws, which is to say that we need to have the model for the pi 2 match the real world, and that we need to have the model for the third pi term match. We need to have all of these pi terms match, dot, 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 including the nth one. And if that's true, if true, then, so it's almost, I wish I had made this go from left to right, but I think I'm copying somebody else's thing. I seem to recall that somebody else had made it this way right here. So I'm going to blame somebody else. So that I say, if these are all true, then we can then take the primary guy and match him up, right? I guess it was probably easier just to say that out loud, but instead of writing all this stuff down. But I want to make it really clear that that these have to be true, and as soon as they're true, then we can proceed and let these things run out. So we have a number of things, different situations. They could be quite complex with a lot of different variables going on. So we want to take as best we can to look and analyze what these things. What these pi terms might be and how we might go about them. I think I have some relevant slides. Boom, right there. I just said all of that right there. And okay, so here is something, the principles of the similarity, right? So this is really stating what I just said in a different way, which is what restating means. There's three necessary conditions for a complete similarity between a model and a prototype. We have geometric similarity, and that's the one it just makes sense. It's a scale model. We often think it's the geometric scales, right? A lot of times it'll be the same proportions and that type of thing. And that often will be what we consider the main scale factor, or a lot of times that's what we'll principally say. We also need kinematic similarity, which means that the velocities at lots of different points should be proportionally to each other at some kind of scale factor, right? It doesn't necessarily have to be the same as the geometric scale factor, and we'll see why that is. And then we also want dynamic similarity, where the forces are also scaled. Now, this, by the way, once again, we're doing the pi terms so that the forces aren't necessarily going to be the same scale as the geometric scale or the kinematic scale. The way that they are scaled are based on the pi terms. Okay, so let me go through this big mess by one thing at a time. So here is sort of the big idea. And so we're using a typical type of drag situation. And so drag is a pretty common thing that we go. So we're going to take this drag force, and we're going to say the variables that we would use would be the width of this, the height of it. We'll also have a wind velocity. We're going to have a density, and we're going to have viscosity. Anything more? I think that's it. We might get to like roughness or something over there. So some other things we could like try to include. All right, so the pi terms are going to be, and this would be after doing a Buckingham pi, so we're just going to assume that we did it. We have this ends up being the primary pi term. And the ones that are sort of like the dependent ones, well, one of the obvious ones is the width over height, right? The scale of this, the proportions of this thing are, that would be the geometric sort of, well, it's not the scale, but it's really the proportions. We'll see in a second. This will come out, and even though this doesn't have a D or an L, this is Reynolds number right here, right? So we'll just see the Reynolds number naturally comes out when you have density and velocity and viscosity and some dimension. And so this will be, a lot of times we'll call this a characteristic length, even though it's the width, right? And that comes from experience. If you have multiple dimensions, which one will be the characteristic one? So what we're really saying is if the width to height ratio of the model equals the width to height ratio of the real thing, and if the viscosity, the Reynolds number of the model matches the real world. So both of those things have to be true. If that's true, and by the way, let me point out to you that these things can be used to make a scale, right? So we could say that we have the velocity of the model. So I'm putting this m to the subscript, so that could be have the proportions of, like, we're going to mix this thing up, right? Put an m's next to all of these and mix them up, and you would say that the viscosity ratio to the real world, the model of the viscosity to this, and then the density and the width times the velocity, right? So we could find what velocity that we need for our model based on these proportions, right? And so we might we'll look at this in a second. We will call each of these terms lambdas, but I didn't want to jump into it just right away. Well, let's go ahead. Usually, what we end up saying, we'll call this a lambda, because usually the model on the top. So this is going to be the lambda that's based on viscosity, the scale of the viscosities. Here's going to be 1 over the scale of the densities, because the model's on the bottom. And this right here is also going to be 1 over the width scale right there, right? So we have scale, 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 and these are going, but these are determined by the Reynolds number. So if we match this right here, right, then we can match this guy right up here. Let me and v squared, right? So that's the model, and here's the real one. Or we could write or written, so this is just writing in a different way, that the actual drag is going to be found from the ratio of the widths of the thing, because this is the most important characteristic relationship, and the densities ratio and the velocity ratio. But you can see that this is by the square. These are by the square, but that's not by the square onto the thing. So these are scales, right? These are different scales, but the most important scale is usually this one right here, of course, but this was actually the inverse of what we typically thought of as the scale. So here's what we consider the scales. We usually have the model on top, right? So like if the length scale is the one that's probably the most important to us, and they're just showing a length right here. But we could see that it's going to be the width scale would be the one that we would consider that, because that's the geometric scaling, and this would be the kinematic scaling. And truth be told, this is sort of although it's viscous forces, these are really sort of force scaling, to a certain extent. Really, right here, this is the force scale in this respect. So we would write this thing out as a lambda w to the -2, right? Because this is upside down, right? The model's on the bottom, but it's squared. And then we would have a lambda rho to the -1, because it's upside down. And then we'd have a lambda v to the -2 and times our model, right? So if we end up getting, if we measure this drag and we knew all of these different scales, we would say that means here is the predicted drag from that operation. The truth is, though, we can't always get this. There's nothing that guarantees that this will actually work. We have to test and verify, and we could be let down. Perfection's unobtainable. And sometimes we're left with what's called a distorted model, where it's not possible to get all of the scalings. And the most common one is for ships, or it's a common example, where we cannot get the Reynolds number scaling and Froude number scaling at the same time, because most of the time we're limited by what fluids we can use, right? So here is the Reynolds comparison, but if we have the same fluid, water usually, that means these guys are the same, so they could cancel out. So what you're left with is a velocity times the length of the model and the velocity times the length of the real thing. Well, you could take a ratio of those, and if you found a ratio, let's say that was 100, okay, let's just assume that, for instance. So that's nothing. There's nothing that says it's going to be 100. We're just saying hypothetically. Let's say it's 100 scale, right? That the real one is 100 times the model. Well, if you do the Froude number, news, we're stuck on Mother Earth, so G is the same. The gravity is the same, so that's going to cancel out there. And so now we have the velocity over the square root of L and velocity over the square root of L. Well, that's going to turn into 1/10. So you can't have a scale that's 100 for the model. So the model's going to be 100 times the real thing, whereas this model is going to be 1/10 right here. Well, the good news is that for many times for many ranges, the Reynolds number, the viscous forces, aren't nearly as important as the free surface. That's what Froude number represents, the free surface, where it has gravity trying to keep the water flat, and you're trying to move it out of the way, so you're fighting gravity. So that's like the physical meaning behind the Froude number. And so that a lot of times that's going to be important. But we also have to do workarounds that are possible to be able to get around this this thing. So sometimes it might be a little more complicated than we need to discuss in our class, but we will find that it's possible back out, like to take data and then from that data be able to like extract out what the influence of the distorted model was to correct the data. That's as much as I would want to go into that for towing tank tests. So there's a lot of common typical studies that we have, things that show up, and one very common is flow through pipes and ducts, and we find out we might have a primary pi term. So let me write that. That's what I mean by this, and I'm just not going to say what it is, right? A primary pi term that we want to get to, and it will be dependent. Let me see. I meant to write it's a dependent thing. It's dependent on some type of length or a bunch of different length scales, right? So this is Li, meaning an index of a bunch of different lengths. Often roughness, per some length, characteristic length is what we usually talk about it. And then also Reynolds number shows up. This also happens for immersed bodies, or maybe airplanes, golf balls, cars, when we're trying to get drag or lift out of the thing. And we have the same thing that goes on right there. So I could have just put it for both of them. But there can be, a lot of times it'll be the different characteristic dimensions. Like this might be the inside diameter, while this might be the wingspan over here, this characteristic dimension. Or it might be the diameter, outside diameter for a golf ball. It's just a length term, and from experience we determine what it's based on. And then for things with free surfaces, where it might be ships and rivers, and if we're trying to analyze flooding or that kind of thing, we have the characteristic length, so we might have a lot of them, and we could have roughness, but we're going to also have Reynolds number, but we also might have that Froude number because gravity is working against me. John Mayer told me that. And we also might have surface tension, might even be a thing, because a lot of times it's not, but maybe if we're a small enough scale, we would worry about the surface tension, which is called the Weber number. I think I got that right. So you'll see that we have RE, Reynolds number, Froude number, and Weber number. And we're 17 minutes into this, so let's see what we can wrap it up. Here's some pictures, pretty pictures of like a wind tunnel. You can see like this smoke coming in here. There's and other ways that we could analyze and see the streams going along here, but also measure the drag that's required. This characteristic velocity, characteristic length, characteristic velocity, characteristic frequency, all produces these variety of these non-dimensionalized parameters, and they can actually be used with the differential equations, but we're not doing that in this class. Here's where we describe the validation of the model and the fear of having distorted models, and the towing tank's very, very common one. I'm not sure where the force block is. It's probably in here, but we have something called a force block in a towing tank that helps us to measure the thrust, or the drag, I should say, from this. But the Ali Burke Navy Fleet destroyer hull form is a very classic one. Very classic hull form. There are a lot of ships, a lot of military ships based on that hull form. And this is what we just said. And I think I left out something. I did leave out something in the Weber. I think I left out the characteristic length. So don't forget the characteristic length. So we're going to do this example next class. And the video went a little longer than I like, but it's late at night. It's 10:12 at night, and I need to go home. So I'll make some more videos tomorrow. Let's do that. Good night.